All right, for this problem, we're told that if the resultant of the loads shown, so that's a 10 kip load, a 4 kip load, a 12 kip load, and then an unknown couple or moment that's applied out here at point C, but if the resultant of these loads passes through point B, so point B can be assumed as the roller, determine the equivalent force couple system at point O. Now, before we're going to be able to solve this problem, we're going to have to determine what this unknown moment is out here at the end. So what the problem statement tells us is that when we grab our resultant, and I'll use orange for this, these forces are all vertical, so our resultant is either going to point down or up through point B. But we know that the resultant acts at point B. And so if the resultant acts at point B, then we know that the moment at point B would be equal to 0. Because remember, the way a force couple system works and the way a resultant force works is you replace the loads that you have by a single force and you specify where it acts. And the equivalent to the downward 10 kip, the upward 4 kip, and the downward 12 kip loads, along with the applied moment, is a single force resultant that acts at point B. So since that force resultant, we can call it R, acts at point B, we know there's no moment at point B. All right, so we could go ahead and get R if we wanted. R is pretty easy. We can look at this one. We have 12 kips down and 10 kips down. That's 22 kips, and 4 kips up. So we know that R is 18 kips. And it is directed downward the way that we have shown it. Okay, now, as far as determining what this moment is, since we know that R acts at this point above B, we know that the moment around B has to be 0. So that would be the moment made by all of the applied loads. We can call counterclockwise positive or clockwise positive, it doesn't matter. For this problem, I'm going to make clockwise positive, and I'm only doing that because this M is applied clockwise, and I can put my unknown in as a positive. But again, that does not matter. Okay, so the 12 kip force makes a moment around point B. It is 3 feet away, and it's going to produce a clockwise rotation. So we have a positive 3 times 12. We can go ahead and add the M. The 4 kip force will also make a moment around B. It's going to create a clockwise rotation around point B, and it has a moment arm of 3 feet. So we have plus 3 times 4. And then the 10 kip force will create a moment around B. It is 7 feet away, and it's going to create a counterclockwise, which for us we have called that negative in this instance. So minus 7 times 10, and that's equal to 0. And if you do the math here, we add these values up and solve for M, we would find that M is equal to 22 kip feet. We do get a positive number for this. It has to be kip feet for the units because our forces were in kips and our dimensional lengths are in feet. And since it is positive, we know that the value is clockwise. So we know M. Now please don't think that this M is the same as the couple that we will need at O. This is an applied load, and we'll now have to compute the moment made by our system of forces at point O. So the problem statement telling us that the resultant has to pass through B is a piece of information that we use to determine M. Now that we have M, we'll have to find a new moment made by the 12 kip, 4 kip, 10 kip, and the applied couple of 22 kip feet, but we'll do it at point O. So our resultant will not change. That's still going to be 18 kips down. And now all we have to do is compute the moment that we have around O. And again, we can take clockwise positive. So at point O, the 10 kip force will have no effect since it passes through. The 4 kip load is going to produce a clockwise, or excuse me, a counterclockwise moment around O. So we'll have 4 times 4. The moment arm is 4 feet for that load. The downward 12 kip force has a moment arm of 10 feet. It's 12 times 10, and that force is going to produce a clockwise moment around point O. So we'll have a plus, excuse me, this counterclockwise was minus, so minus 4 times 4. So plus 10 times 12. And then I have an applied moment M, which I know is 22, so plus 22. And that is equal to a value of 126. So the moment around O is equal to 126 kip feet clockwise. Now, just so we're clear, around point O, the 4 kip load makes counterclockwise, which is negative for us, and the 12 kip load makes clockwise, which is positive for us. And the moment, even though it's applied at point C, I simply add it into this expression. A moment has the dimensions, you'll notice, of kip feet. So what's common is a lot of times people want to multiply the moment out here by this distance. But if you were to do that, you would have kip times feet squared, and that wouldn't be a moment. That would be something different. So moments are free vectors. They're simply added, and even though it's applied out here at C, it has the same effect over here at point O, because all of our structures are, of course, rigid. So the force couple would have a downward 18 kip force. We can sketch this quickly. We'll go with let's go with an orange color, actually, since we have a 10 kip load out there that's red. So we've got a downward resultant here, R equal to 18 kips. And then we would have a clockwise moment, MO, that's equal to 126 kip feet. And so the downward 18 kip force and the 126 kip foot moment would be equivalent to the 10 kip, 4 kip, 12 kip, and applied moment M on this beam. And that's it for this problem.